All right, good. That'll keep us busy for a while. Let's tackle these. Let me see what might be the best to tackle first. A good warm-up would be forces. Let's start there. Okay, just as a quick overview on forces. Okay, there's 4 forces that I want you to be familiar with, and that's the ionic. This is really an intramolecular. And then there's the H bond. And the dipole. This is a permanent dipole. And then London. So you want to know those forces. You want to know that they increase in strength going this way. So ionic is the strongest, and I've listed them in order. You'd want to know that. But you also want to know as molar mass increases, London force increases. So London force could overtake dipole or the H bond. Okay? So we've got that. So remember to consider molar mass. I'll put an M there so you can remember that. Now, as the force increases, then there's a couple things that you'd want to remember. That would increase the boiling point. So this means you're comparing 2 items. So the right-hand column means I'm comparing 2 items. I know the forces. I want to see which one, say, has a higher boiling point. Force increases, you have the higher gamma, which is what? Surface tension, viscosity, and then lower vapor pressure. Okay? So those are the correlations that you want to be familiar with. Once you got these in your head, or I would say when you enter the exam, write this down first before starting the problems, and then you won't have to keep it in your brain waiting until you get to that problem. Okay, so a typical thing would be, let's try a couple examples just so you can see how this would work. I'll give you 2 molecules like this, okay? You want to, and I would ask you something about the physical properties, which is the right-hand column. So let's try gamma. I want to know which one has the highest gamma, and I'll circle that one. So first thing you'd want to do if you're asked about this is you take a look at the molecules. You can start with either one, but it'll be the same answer in this case. And what I do is just go from top to bottom in forces, okay? I think that's the easiest for me. So first I ask, is it ionic? You say, no, there's no metal. Is there H bond? No, because there's no nitrogen, oxygen, or fluorine connected to a hydrogen. Dipole? No, it's fully symmetric. Everything has London, so by default they both have London. So the one with the higher force will be the one with the higher molar mass, which is the one on the right. So that one will have a higher force. Because that one on the right, nitrogen, has a higher force, it'll have a higher gamma. So the one on the right has a higher gamma. Okay, let's try another one. Okay, let's try this one. Now we go again from top to bottom on the left-hand column just to figure out which force is dominant. Okay, so that's what the left-hand table is for, which force is dominant. So, first you ask, is it ionic? No, no metal. Second question, is there H bonding?
Yes.
One of these does. So you look at, they both have oxygen. If you see an oxygen, a nitrogen, or a fluorine, you want to see, is a hydrogen attached to one of those? Not here, there's no hydrogen on this oxygen, but there is on this oxygen. So the one on the right is H bonding as the dominant force. The one on the left, which one? The one on the left has what dominant force? It's dipole, actually. How I knew that is this has 2 lone pairs, or a neutral oxygen will have 2 lone pairs, it goes from 2A. And that's just like water, it's bent. Because it's bent, the one on the left, dominant force would be dipole, the one on the right would be H bonding. So you just look on your list on the left, H bonding is a stronger force in general. So the one on the right has a stronger force because H bonding is stronger than dipoles. Because it's a higher force, it'll have the higher gamma. Okay? Yeah? Yeah, that's right. So the question was, are we assuming they're liquids? Yeah. So anytime I would give you a question like this, you're assuming they're liquids. However, I think on the upcoming exam I specify. Yeah, so, but yes, they're liquid or aqueous or something like that. By the way, are the people here not in my class? Okay, hey you fools up there. Okay, what class are you in? Chubadakis and Kramer? Hayashi? Oh, it's random. Okay, welcome. I assume they're teaching the same thing as I am, because this stuff should be on the final too. Okay, let's try one more. I want to keep this one the same. Okay, so we already know, I'm keeping the one on the right the same. This has H bonding. We already determined that. The one on the left, however, has what dominant force? It's ionic. Ionic is stronger. Automatically, you're going to circle the ionic one. Okay? So that's forces. You'll be asked what's the dominant force, or you'll be given two or more items and asked what's one of these physical properties. Nobody asked me, but just as a side note, another common question when you have two items is, are they soluble in each other or are they miscible? So if you have a question like that, you'd want to find out things that have dipoles would be miscible or soluble in each other. Things that don't have dipoles, non-polar, would be soluble in each other. But a polar and non-polar wouldn't mix. So for example, would these two mix? Yes, they're both non-polar. They would mix, yes. They're soluble in each other or they're miscible. And then kind of to attach to these of course don't have to be liquids. They could in the question that you asked me earlier. These two on the top are typically gases. But this would work also for, it wouldn't make as much sense for surface tension, but they could be liquids. Okay, what was I asking? Oh yeah, are they soluble? How about these two? Do you want to ask, are they both polar? Okay, is this one polar or non-polar? This is polar, yeah. Pretty much anything with H bonding is probably going to be polar. Okay, if you didn't know that. How about this one, polar or non-polar? Polar, it has a dipole. Anything with a dipole. Really, in this list, the main one that would most likely be non-polar is the London. If something only has London, it's likely to be the one that's non-polar. Okay, so these would mix, the top ones would mix. How about these two? They would mix, yeah, they're miscible because that one's polar, and it's ionic, and that one is. So if I would make a little note up here, these three are likely polar, but they don't have to be. And the bottom one is likely non-polar, but it doesn't have to be. I'll put NP for non-polar. Okay, yes?
Could you just repeat the rule again, what you're saying? So if they're both polar or they're both non-polar, then
The rule is like dissolves like. Okay. So if they're the same, they're both polar, they both dissolve each other or are miscible or are soluble in each other. Or if they're both non-polar, same. They mix. But if one's polar, one's non-polar, they don't mix. Yeah, that's according to delta H of solution. Maybe I'll do delta H next. Yeah.
If you're given like a list of molecules and they say which one is the highest or lowest boiling point,
right.
How are you using the forces?
Yeah, the question was, if you're given a list of molecules, which one's given the highest or lowest boiling point? Figure out the dominant force first, and then use this. Highest force, highest boiling point. Okay. Yes?
do you think it's worthwhile for us to know all the polar rules from last quarter really well?
Is it worthwhile to know all the polarity rules from last quarter? That is extremely helpful. Could you get by without it? The only way you can get by is hopefully if you look at it and you can tell if it's asymmetric. If it's asymmetric, it's polar. This one's obviously asymmetric. This one is, that one is. So they're all polar, bottom four. Top two are both symmetric, so they're non-polar. But if you don't remember that stuff, yeah, you should go back to it. Okay. Yes, last one, then I'm going to the next topic. Yeah. Freezing point doesn't have a good correlation here because that's getting into solids. And this is mostly working for liquids. As you see in the top case, surface tension's a little sketchy. I had to make up a question, but it would work. You could do this for like vapor pressure for this one. It would have followed this pattern. Yeah. So these are the common properties we always give, so that's why I listed that for you. Okay, cool. This relates to enthalpy, so let me do a little bit on enthalpy. This all was related to something called delta H of solution. Just a little review if you need a refresher. Delta H of solution, if it's near zero, numerically, that means it mixes. It's called an ideal solution when delta H is zero. That typically happens when you have two nonpolars. Okay? You'll have a small delta H of solution. So two nonpolar things will have a small delta H of solution that will more easily mix. But it also can mix if there's two polars. That's like dissolves like. And delta H will also be small. The bigger that delta H is, either positively or negatively, the less likely they'll mix. Okay? That's what delta H of solution is. But in general, let's be more general now, enthalpy is just heat at constant pressure. So it's still the same heat at constant pressure. Our world is at constant pressure. And so when I say, hey, we're doing some chemical whatever, we want to measure energy, because we're at constant pressure, the energy we're measuring is pretty much enthalpy. If the pressure was changing a lot, you wouldn't see enthalpy for Hess's law, and enthalpy for delta H of formation, and all these places that you see enthalpy, because it wouldn't quite work. But because our world, again, is at constant pressure, the energy we're always measuring is some sort of enthalpy, okay, or approximately an enthalpy. Now, one more thing that I'll mention, I think this is the end of chapter 12, reader. Yeah, this is page 31 if you have it. There's a ton of ways to find delta H. And so if we ever ask you for delta H, I just want to list out all the possible ways you could find it. So the most common ways are the top really 3 to 4. But you shouldn't count out the bottom 2. So let me just go over them quickly, and you can refer to this later. Conversion problem. So you're given a delta H, and it's weird because they give you a delta H, but then they ask you for a delta H because there's an amount involved, like 5 grams or 2 moles or something like that, some sort of amount. You'll know it's a conversion problem. Hess's law, that's the one with all the reactions. We're going to do that in a minute. That finds delta H. When you have one reaction and you're given formation enthalpies, then that's another way to find delta H. Calorimetry can do it too. So if you have a bomb calorimeter or a coffee cup calorimeter, we'll do the bomb calorimeter in just a little bit. That's a way you can actually also find delta H. So that could be Q of reaction for a bomb calorimeter, or just any sort of delta H in a calorimeter problem, like a phase change. So for example, part 5 of the thermochem lab, you find delta H of melting, okay, for ice. Clausius-Clapeyron, one of the typical constants in a Clausius-Clapeyron is a delta H of vaporization, but it could be that and temperature and pressure are changing, but if we give you 2 pressures and 2 temperatures, people in my class are doing the homework, and you did the benzaldehyde example, this was one of those, where you gave you 2 pressures and 2 temperatures, and you had to find delta H in order to do the second part of the problem. That's a possible way. Another possible way to find a delta H is if using the first law. So delta U equals delta H minus P delta V. And so if we give you delta U and P delta V, that's a way you can find delta H as well. So there's a lot of ways you can find it. Remember, it's just the energy. Specifically, it's a heat. And most of energies are transferred in our world via heat at constant pressure. Okay, that was our enthalpy. We knocked out that one too. Let me cross that one off. Nice. Let's do a little bit with work before we go over to Hess's law. Okay, work. There's a couple things I want you to know about work. Okay. So let's say you had, well, let's write out the first law. First law is this, Q plus W, and Q at constant pressure is delta H. Work is minus P delta V. So you could see work involved in a first law problem. And a really simple version of this, and I'll tell you a more complex version, a really simple version of this would say, let's say you have a system, SYS for system, and let's say 5 joules of heat is given off. And let's say that 2 joules work is done by the system. And so there's a work involvement, and I want to know delta U. What's delta U? Well, in this kind of problem, it's just about signs, okay? Plus signs and minus signs. So what you would do is 5 joules of heat given off. Is that a positive or negative number? Negative 5. Heat, remember heat, that's the Q term. So that's the first term. And then now to work, the second term, plus work done by the system, plus or minus? Yeah, work done by the system, that's a negative, so that's a negative 7 joules is your answer. So that would simply be that. That's one kind of work problem. Another kind of work problem is just solving for work using one of 2 formulas, either this one or this one. Nope, not that one, that looks ugly. Negative delta N RT, okay? This is 2 different types of problems. It depends what they give you. If you're given pressure and volume, you of course use this one. If you're given temperature, and what I would say is a reaction, you would do this one. So temperature and reaction, you would do the one on the right. Pressure and volume, you'd use the one on the left. So literally, it's plug and chug on this one. So let's go to the left one first, and let me say a little bit about it. Let's say on the left, you'd be given a pressure, let's say 1 atm, and some sort of change in volume. Either you'd have to subtract yourself or we just give it to you. Let's say it's 2 liters. Now, to do this kind of problem, you say work is minus 1 times 2. But negative 2 would not be your answer. Why not? Negative 2, this is, I'm not done yet. I have to do one more thing. Yeah, the wrong units. This is in liters, atmospheres. Liters, atmospheres, I need this in joules, so I need a conversion when it's this type of problem. So there's always going to be one more step. And I believe, yeah, it's 101.325. This will be given on the exam, joules per liter atmosphere. So that's one type of problem. You just calculate that out, whatever the heck that is. That's your first type of problem for this equation. Now, the other type of problem would involve the part on the right-hand side, this. We would have to give you a reaction, okay? So let me write a reaction here. It's 1 N2 plus 3 H2 goes to 2 NH3, okay? And then I want work. And let's just say the temperature is 25 degrees C. So in this kind of problem, because it's a reaction, and you're given a temperature, then it's definitely have to use a right-hand equation. Work let's skip change in N for a second. I'll do that in a moment. R, okay, let's skip that one. T is the easiest. Okay, let's do T. T is what? Yeah, 298. 25 plus 273 to change it to Kelvin. Okay, let's do R next. What R am I going to use? Yeah, you're going to use the 8.3145 because that has joule units. And work is a joule unit or a joule variable. So 8.3145 joules per mole Kelvin. Zoom in so it's easier to see. Okay, now, before you can find change in N, which is moles of reactants minus moles of products, you'd have to ask me a question about the reaction. What do you need to know about the reaction before we can find N? Are all those gases? Because this only works for gases. So I would say yes, in this case they are all gases. On an exam they would definitely be labeled. They're not, ask your TA. But this delta N is only for gases. If you see a liquid, a solid, or aqueous, ignore those for N because we want moles of gas. Remember, it's from the ideal gas law. Okay, so in this case, what would be delta N? 2 minus 1 plus 3, or 2 minus 4. Okay, so that would be work in this case. So either the common work questions are this. one of these two that I just did, or a combo problem where it's one of these two comboed with one of these problems up top. Okay? That's really all you can do with work. All right, I'm going to move on. Yeah?
So if we were a gas, like who's a gas and a liquid, or just another from
Yeah, you want to say like, let's say this is a liquid. Okay, if this was a liquid, what's delta N? Anybody? 2 minus 3, which is minus 1. Is that okay? Yeah, so you just ignore it totally. Okay, let's go back here. Okay, what was I doing? Oh, I just did work. Let's do the bomb calorimeter. Okay, just making our way through. I think we can finish everything. Bomb calorimeter. That's where you have a calorimeter. You don't really care about the mechanics of it. You just know there's water inside and a couple different instruments inside, like a stirrer and a thermometer and things like that. So this is your system. And typically, but it doesn't have to be, it involves a combustion reaction. But really, anything that is exothermic. So really, in general, in the exothermic reaction, usually a combustion reaction. Okay, so let's try a made-up reaction. Perfect. Okay, A plus B goes to C. Let's say delta H is negative 100 joules for this reaction. Okay? And let's say C is 1 joule per gram degree C. Oh no, there wouldn't be the gram there, sorry. Because it would just be heat capacity, not specific. So in this case, this is really a plug and chug sort of problem. They would ask you in this case, what's delta T, or what's the temperature increase? And so all you would do is say, well, Q equals C delta T. You can just take the energy they gave you for the reaction, in this case, 100 joules, equals C, 1 joule per degree C, and that'll give you the temperature change. Okay? The negative, you could just drop out because you know it's going to be exothermic. And so you can just take the absolute value of Q in this case. Another kind of question, it's all plug and chug for this one. Another thing we could do is we could give you C and delta T and you would find this one. If you had that sort of problem, so like, let's say, for example, we gave you delta T is 100, okay? And we gave you C is 1 joule per degree C. And we wanted Q, okay? The way I would write it out if we were going the opposite way would be this. Well, the sum of the Q's equals 0. And that's the Q of the reaction plus the Q of the calorimeter. Or Q reaction equals minus Q cal. Or negative C delta T. There's where the negative sign pops in. And that would be negative 1 joule per degree C times 100. Now typically, this looks like just minus 100 joules, which could be fine. That could be your answer. However, sometimes they'll say, what's the energy per 2 grams of reactant? Okay? So that would be, in our case, A. Okay? So let's say we had 2 grams of A. 2 grams of A. And I wanted to know the energy, or Q of reaction per gram of A. You would just take one extra step, and this is not unusual to happen. And you just divide by 2 grams. And so you get negative 50 joules per gram of A. So it's pretty typical on a bomb calorimeter, but not always, that they give you an amount, and you divide by that amount to get your final energy. Okay, cool. That's all I have for a bomb calorimeter. That should hopefully feel like the easier of the 2 calorimeter problems. Okay, now I need to find a Hess's law problem. Unless somebody has one, I need to look for one. So let me look and see if I can find one. But yeah, you could definitely expect some sort of Hess's law problem. They're so needed because especially on the second exam, you'll see them again. They pop up, even though you hate them, they keep popping up. Okay, let's see. Hopefully I'll find one. But please, if you find something before me, just tell me. Oh, wait, is that one? No, that doesn't work. I did that one in class. Oh, wait, I have one in my lecture notes. Are you okay with a hard one? I have one of my lecture notes that's a little painful, but if you can brave it, it's one of the hardest ones I've ever seen, but it's not undoable. It just freaks people out. I guess it could be harder, but whatever. It's good enough, right? Okay, from my lecture notes, let's flip over here. Where did I? Yes. Oh, yes. Oh, good. You haven't seen this one, right? Unless you saw it on my YouTube. I don't think I did this one in class. Okay. So you have 3 reactions. You can write those down. In this case, I just listed delta H 1, 2, and 3 in general. So we're not going to get a numerical answer. We'll just get delta H in terms of these 3, quote, givens over here. Okay? And then I have the problem with this, why it's difficult for a lot of students, is I don't give you the overall reaction. Okay? I typically would, but in this case, we want to make it more exciting. Okay, cool. But I can tell you on our exam, what is it, 1? Yeah, I will give you the overall reaction. Okay, cool. I remember another instructor last year gave one, and there was like 5 reactions, but there was like, I think the students found like 5 to 7 different ways to solve it. It was pretty interesting. Okay, let's try this one. Okay, here's how I would tackle this. Write the overall reaction. Okay, I would do B first. What's the intermediates? And you can kind of start with A, but A is going to be a little bit difficult. You know you're starting with manganese 4 oxide. That would be MnO2. And you know you're producing manganese 3 oxide. That would be Mn2, because O is 2 minus O3. So you know that is vaguely part of the overall reaction. I would probably guess that CO and CO2 might be part of the overall reaction, but I just don't know for sure. But because it appears so much down at the bottom, I would guess that it might be there. But you can see there's a lot of other manganese products that are not in the overall, and those will be my intermediates. So let me list those out in a different color. My intermediates are anything that appears down here, up here but not down here. And for now, I'm going to ignore CO and CO2 because there's so many. I don't know if it's going to appear in the overall. But let's look at the manganese. So for example, Mn3O4 is down here but not in the overall. That one's there. MnO. Okay, those 2. So those are definitely intermediates because those are manganese products in the series of reactions I don't see in my overall. All right. Now what am I going to be up to? Well, kind of the tough part about this one, and that's why I've tended recently to give the reaction more often, is it's hard to know what to do with the multiplier. So I'll help you out on this one since this is a little bit tougher. Let's pick one of these 2 and see where they appear down here. So let's take this one. Okay, that one else. So purple circle right here and nowhere else. That's good. I like things that appear only twice. So let's start there. Okay. And let me also note this one too. what do? I'll do a brown square for this one. That appears right here. Okay? I could really start with either of these. You'll see if you're pretty sharp and you try this for yourself, you could get slightly different multipliers. But I'm not going to deal with that. I'll just pick to start with the Mn2O3. You could have started with the other one. That's totally fine. All right. So I don't know how many of these I have, but I know they're in the products. So what am I going to do? Then with this one, I'm going to multiply by a negative for sure. And since in this case I didn't know how many in the products I had, I'm just going to multiply, I'll just flip it. Multiply by a -1 for now. Okay, so I'm just going to flip it. This one? Is that what you're talking about? Yes?
Yeah.
Yeah, we'll get there in a minute. Okay. Now, let's see. I'm not going to do that one yet, though. Let me work on the intermediates now, because let's get a different color. So I'm going to pause before I get to the MnO2. Let's work on, let's see, what's a different color? It's pretty seeable. Let's do blue. Let's do that one, okay? I want that one to cancel, all right? So if I want that one to cancel, right now I have -2 of these over here. So what do I need to multiply this one by? Remember, it has to cancel. I'll let you think for a second. It's not 2. Yeah, if there's -2 on one side of the arrow, I need to multiply by -2 right there. Okay? So there's -2 here, -2 there. Those two should cancel. All right. And now I want to work with the final intermediate. This one right here. I'm running out of shapes. Triangle. There we go. Okay. So right now I have how many of these? -6, so I need to multiply that one by. All right. Was it positive or -6? Positive? Okay. Sounds good. All right. This whole kind of fun that I was having here is going to give me how many MnO2s at the end? 6, okay. How many Mn2O3s am I going to have? How many? Yeah, it's going to flip this 3, so I have 3 over there. Okay. Now let's see what happens to the COs. Okay. How many COs, if any, will I have? Yeah, I'm going to have 6 minus 2 minus 1. So I'll have 3, is that okay? All right, let's add those in. Is that okay? That's 3 CO. How many CO2s, if any, will I have? Also 3. 6 minus 2 minus 1. Where was I? Did I say 3? Yeah. Okay. I could simplify my reaction a little bit if I wanted to. How would I do that? Yeah, I could divide by 3 if I wanted to. But I will just, let me rewrite this. MnO2. I rewrote O. Okay. CO2. Let me write delta H just for this reaction as is. I'll call it delta H total. It's 6 times delta H1 minus 2 times delta H2 minus 1 times delta H3. Okay. just to ask you, if I take the overall reaction and divide through by 3, okay, to simplify it if I wanted to, what would happen to my delta H total? I would have to do what? I guess I'm thinking more simply. I'd also have to divide by 3. Whatever you do to the reaction, you have to do to delta H. So if you wanted to simplify, you'd have to do the same thing to delta H. Okay? Cool. If you can handle that, that was a pretty tough one. Again, I would usually give you this reaction on an exam, just a little degree of toughness. Okay? Cool, that was Hess's law. I'll leave this up here if you're still writing that. I'll move this out of my way. And let me move this. So Hess's law, I just recommend you do a couple practice problems just to make sure you get it. Check the ones out in my practice exam reader and that are online. I have several Hess's law. I have Hess's law 1, 2, and 3. And then I have simultaneous reactions and simultaneous reactions 2 and 3. Okay. Let's go on to another one. Hess, we got all those knocked out. Let's try a density problem. Okay, first, what do you need to know to do a density problem? I'm going to call your attention again to the lecture reader. Specifically page, let's see, let me find it here, page 29 at the top. You really need to know, specifically, first column, of course, all the names. You need to know the atoms per unit cell. The coordination number is just something to know, but it's not involved in a density calculation. But it's just something you can see it on a multiple choice question. And then the length, okay? So to do a density calculation, you need this number right here, and this number right here, or this formula. You wouldn't need this. This is just the cube of the length cube. And then the only place you'd see this is, say, on a multiple choice problem. You'd have it say, oh, it's HCP. What's the packing structure? There you go. Oh, AB, AB. Okay. So, assuming you know that, this is how a problem would work. You would say, well, density is mass over volume. Mass is going to be the atoms per unit cell, which is a number you should know. It's the first column there. And you'd want to convert this to grams. So you do that by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. Okay, that's just Avogadro's number. And then you'd use the molar mass, grams per mole from the periodic table. Okay, so this is from the periodic table. Just need the molar mass, so you need to know the compound or the element, whatever it is. The volume is just going to be length cubed, and as long as you know the length, you just cube it. So what I'd recommend, I think the easiest way for most students, take, get R, that's what we're going to give you, the radius of the whatever, the entity, and convert to centimeters. After you convert to centimeters, then I would take the length cubed. This will give you a density in grams per centimeter cubed, which is typically the units we're talking about. Okay? So a straightforward problem we'd give you radius, and we'd give you the compound with its packing structure, you'd find density. But I think if you're in lecture, Josh did he do the foot and mouth disease problem? Oh, wait, let me double check here. Because that'd be a good example if you haven't seen it yet. Let me show you, see if it jogs your memory. Did he do this problem? Okay, we'll do this in a second, but it's asking for the molar mass. I just want to look at the formula one more time. Just to do a different kind of problem, we could give you density, we could give you radius, and you need to find mass and ultimately, in this case, the molar mass. So it's finding something inside here. Or another way to do it, we could give you molar mass and you find the atoms per unit cell. We don't tell you the packing structure. So you go, it's just a way to do the problem backwards. But it's the same kind of problem. So let's do this foot and mouth virus problem. Used to be something you see more in the news, but not as much anymore. Yeah, and so this is kind of an interesting problem. I'll give you a little bit to write it down. If you see cc, like grams per cc, cc means cubic centimeter, so centimeter cubed. Okay? So what we want to do, based on what we know, is find the molar mass of this foot and mouth virus. Would you expect that to be a relatively small number or relatively big number for the molar mass? So a virus is a biological entity. Probably has tons of atoms in it. So we're expecting a larger number. Any biological entity, lots of atoms, we're expecting probably a slightly larger molar mass. We'll see. Okay. And remember when it says grams per cc, that's grams per centimeter cubed. Yeah, cc is centimeters cubed. Okay, so you didn't see this one in class, right? Okay, good. Works out easy for me. All right. What we would do is I'd write, well, density is mass over volume. And doesn't say it too clearly, but the radius is 90 angstroms. Okay? 90 A. And then, so the length, what you would need to know, because this is BCC, if you're looking at that table in my reader, you would say, well, that's 4R over root 3. That's what BCC is. Okay? So the length would be, let's find the length. It's 4 times R, 90, divided by root 3. That's going to be 208 angstroms. And then I prefer to change this to centimeters now, but you could cube it first if you prefer. That's fine too. So and I'd have this conversion on the exam. 10 to the 10 angstroms is 100 centimeters. Okay, so really 1 meter is 100 centimeters, and 1 meter is 10 to the 10 angstroms. So that'll change you to centimeters from angstroms. And then volume would be length cubed. And I calculated that. I got 9.0 times 10 to the minus 18 centimeters cubed. Again, it's just the length, just this number cubed in your calculator. That's a common mistake that students don't know how to use the cube function on your calculator. Make sure you know how to do that before the exam. That's a common mistake. All right, we've got volume. Now, let's kind of take our next step. I'll change colors here to black. If I take the formula up at the top, mass is density times volume. I want to solve for mass because inside mass is the molar mass. So density is 2.8 grams per centimeter cubed times the volume, 9.0 times 10 to the minus 18 centimeters cubed. Okay, so the centimeters cubes will drop out, and all I'll be left with is grams. Move this out of the way. Okay, mass also equals body-centered cubic. How many atoms per unit cell? There's 2. So this also equals 2 atoms per unit cell. If I multiply by Avogadro's number, I can change to moles. Okay, and then the big awesome thing I wanted to find, molar mass. I'll just call it capital M, grams per mole. So now, this up here, the first line, equals the second line. I only have one unknown, and it's capital M, or molar mass. Molar mass turns out to be 7.5 times 10 to the 6th grams per mole. And it's as we expected. It's a virus, it's a biological entity, it has a very huge molar mass. Okay, any questions on that one before we move on? Yeah?
I have a question about the 90 angstroms. Does the question mean that as the radius, or is that the part length across?
Yeah, I noticed I didn't specify that too clearly, but I intended it to be the radius. On the exam, it's specified pretty clearly. Yeah. If you had a question, if you weren't sure, I would definitely ask the TA. Yeah, just for a specification. All right, whoa, this does not want to stay there. Okay, does not want you to copy it. There. Cool. Okay, let's move on. See what else we got. We did density. Let's do a little bit of Clausius-Clapeyron. Let me write it down first. The natural log of P2 over P1 equals delta H of vaporization over R, 1 over T1 minus 1 over T2. This would be something that would be given. It's really a plug and chug sort of question. If you want to see a really tough one, take a look at the benzaldehyde one on the homework. Yes, some people are agreeing. If you're still trying to solve it, remember I have a YouTube video on that one. So just watch the video and just do whatever I do. I think I already had said that in class, right? No. I'm pretty sure. I said, oh my God. Okay. I am fairly sure, but nobody remembers but me, unfortunately. I also mentioned there's a tough mercury one on the homework, and that one's also one of the heat problems. Okay, a few people remember that besides me. Okay, all right. So remember, sometimes I have the homework problem solved on those YouTube videos. All right. So, like, let's say we wanted the vapor pressure of water at 75 degrees C. Okay? Let's say that was my question. What's the vapor pressure of water at 75 degrees C? Well, because we're working with water, there's a couple things we know. First of all, we know the normal boiling point. What's the pressure at the normal boiling point? 1 atm, and this would be 100 degrees C or 373 degrees Kelvin. Okay? So I have the pressure and temperature. The vapor pressure of water and some of the delta H values for water are given on the back of the exam. So make sure you know that they're there. And I believe delta H of vaporization for this one equals negative 44.1 kilojoules per mole. Okay, so now we can do our calculation. I will call these somebody pick a number, 1, okay? And I'll call these 0.2.
Why is it negative?
I don't know. Is that a problem? It's positive. That's good. Let's think about that. Delta H vaporization. I'll ask you so I don't have to think. Is it a positive or negative number? Okay, there's a vote for positive. I'm not saying it's wrong or right. I'm just asking. Would vaporization be a positive or negative? Meaning, are you putting energy in or are you taking it out?
Taking it out.
You're going from a liquid to gas, that's right. So you are in or out?
In.
In. So then is it positive or negative? Good. Thanks, man. Okay, was that you? That was you. Okay. I don't know. Nobody's taking credit, but I'll give it to you because you're looking at me. Okay. Good. So the natural log of P2 is what we want to know. P1 is 1 atmosphere equals, remember this is kilojoules, so we need to go 44,100 joules per mole. R is the 8.3145 joules per mole Kelvin. And then T1 over T1. T1 would be 373. And 1 over T2 T2 would be 75 plus 273. And you'll notice we only have one unknown, it's the P2. Since I just made it up, I don't have an answer for it, but whatever the answer is, it would be in your calculator. Okay? Cool. So it's just a plug-in sort of question. Remember, point 1 I just knew because I needed an extra point, and I know the normal boiling point of water. If it's something besides water, then they would say the normal boiling point of blank chemical is whatever, 400 Kelvin. So you know temperature, and then the pressure, since it's the boiling point, would be 1 atmosphere. Yes, I'm frozen. Listening to you. Where is this? If it's something besides water, it'd be given in the question. If it is water, it's on the back of the exam. If you're taking my exam.
Okay.
Yeah, if you're in my class. You're in my class. Yeah, okay, cool. So back of the exam if it's water. So make sure to familiarize yourself with the back of the exam before you get into it. Let's do some, I guess, colligative properties. Colligative properties kind of work like this. Okay. There's 2 formulas. Of course, we give them to you. Pi equals IMRT. Shoot, I think that's positive. Yeah, that's positive. And then delta T equals IKM. Okay. In the first equation, this is a capital M, so that is what is capital M? Yeah, molarity. And then this is lowercase m, molality. Okay? So that's lowercase m, that's molality in the second equation. Okay, the person, which one of these did you want to know about, or both? I don't remember. We're getting both? Okay. These are basically just calculations. The top one tends to be an easier calculation. It's kind of like the ideal gas law, where pi is a pressure, but it's a certain type of pressure. It's the osmotic pressure. That's why we use a different variable for P. We use the variable pi. It's not 3.14, it's just a variable. Okay? It's not a constant. And so all you do, since this is the ideal gas law, you're going to use this 0.08206 here. Again, remember, ideal gas law, more convenient to use that R. And you just plug in temperature and molarity. That's it. Okay, I'll get to I in just a minute. Okay, the bottom one, usually for students takes a little more thought, but the calculations are still similar. Did you already do the colligative properties lab? Yeah, so if you've done that and you've done the calculations, that's pretty much the same as what you've done there. So you've already learned it, really. K is a constant. This has to be given. Okay? And then molality, remember, is moles of what? Solute, solvent, or solution? Solute per kilograms of solvent. This is the only one I can think of right now that is solvent in the denominator. Typically the denominator is solution. Okay, but this one's solvent. Okay. Okay, let's drink a little of the Kool-Aid right now. Okay, that's molarity, you got that. This bottom one represents a temperature change first. Either the boiling point is going to go up or the freezing point will go down. Okay? See, the boiling point will go up. If you imagine a phase diagram like this, looks something like this. When you add a solute to a liquid, let's say you had water, and you put salt in it, what happens to the phase diagram is it drops down. Okay? Why is that a big deal? I don't know, because I can't find my blue pen. Here it is. Oh, gosh, now that looks ugly. Oh. Okay, try again, try 2. Okay, and then it drops down the phase diagram like this. Okay, hopefully this will look more beautiful. And I'm going to draw a horizontal line right here. Oh, Okay. I don't know. Okay, one more time. If I can't get it, we're just gonna not learn the concept. But it still will be. All right, here we go. It drops down. Okay. All right, I'm going to attempt again to draw a line. Yes. Okay, that's what I meant to do. Okay, do you see that point right there? That is called what point where the tip of my pen is? That's the boiling point, because we have a liquid here and a gas here. See how the boiling point goes up? See how it's much higher in temperature now? So the boiling point increases that direction right here. Remember, this is pressure and temperature for the phase diagram. It's going up. What's this point called? Freezing point or melting point. It's going to go down to where the black line is now. So it's going down in temperature. That's what colligative properties does. Or adding a solute drops the phase diagram, increases the boiling point, and drops or depresses the melting point. That's why when you de-ice a plane, they're putting the solution on the plane, if you've ever been on a plane in cold weather. Or on roads, they'll add salt, say, to help melt the ice. Okay, so what this does is calculate that change in temperature. All right, now, that we already talked about that. K, do you remember from lab, is K for the solution, the solute, or the solvent? K is for the solvent. Write that down if you didn't know. K is for the solvent. Okay, the one there is more of, solvent. I, does anybody know what it's for? Solvent, solute, or solution? Not really the solution. Not the solvent, it's the solute. Okay, we're close. It's the third guess. It's the solute. I'll show you how to do that in a minute if you're not sure. You're calculating the temperature change for, not the solution. Well, sort of. Really, not. I wouldn't technically say the solution though. It's the solvent. You're calculating a solvent temperature change. So it's originally the boiling point, say, of water, before you put anything in it, say is 100. You put something in it, like a sugar or salt or whatever, the boiling point is going to be above 100. So you calculate the solvent temperature change when you put a solute in the solvent. Okay. So how would you do a problem? Oh, let me talk about I for a second. I really measure, it's called the Van Hoff factor. It measures the number of items in a solution. And so let's take a couple examples here. Okay, like those. It measures, you want to know electrolytes. It kind of goes back to electrolytes. So for example, the top one is not a good electrolyte. If you vaguely remember that from chapter 5, if you have my old 2A reader, the beginning of chapter 5 told you what's a good electrolyte, what's not. It's good to know that stuff for this. So the top one, CH4, is not a good electrolyte because it's a molecular compound. So it exists just as is. These two, though, are ionic. So these are, you got an Al3 plus here and 3 Cl minuses because it separates out in solution. Electrolytes do that. And for this one, it's a sodium and a chlorine. So I measures this number of items in the solution. Here there's just one thing. Sodium chloride, there's two, a sodium and a chlorine. And here there's four, an aluminum and 3 chlorines. So that's how you kind of get to I. You determine if it's a good electrolyte, if it splits up in solution, and then you just count the number of entities, or the number of ions, say. That's where you get I. We'll do an example of this in lecture next time. And I'll tell you this in lecture, but I'll just tell you now. Of these, since it was the newest material, and I heard Josh had to go through it a little bit faster, I'm going to give you easier questions on this. So that you won't really have a calculation, it'll just be easy multiple choice questions. Hopefully after Tuesday's lecture, it'll feel somewhat like a freebie, is what I'm hoping for. Yeah? That's right. In lab, I was 1 because it's organics. Organics or molecular compounds are always 1. Yeah, they're not good electrolytes. That's why you ignored what it was. Yeah, good. Good application. Yes?
Now, the same stuff as the solubility rules, which one like splits apart?
Oh, is this the same as the solubility rules? Sort of, yeah. If it's aqueous, it splits apart. So that's true. If I gave you an ionic compound, but it didn't dissolve, that would be a problem. You couldn't really do this kind of question if it didn't dissolve. So I probably wouldn't give that to you. So what's more important is to know if it's a good electrolyte or not. And that was right about that same section in 2A, which is really determining, does it split up into ions? Okay? All right. What else were we up to? I think I can do one more thing before we go on to specific questions. Would you rather see Henry or Raoult? Okay, now raise your hands. It's too like jumble. Henry. Nobody cares. Okay, Raoult. Okay. Raoult's law. We'll also do an example of this in the next lecture. It says the partial pressure is equal to the mole fraction times the pure pressure. Okay? And let's see, I want to refer to my reader again for this one, because there's some goodies in there. This is page 41 in the reader if you want to refer to it. A couple goodies in there. Okay, this is a pressure of a gas. Okay, this is the mole fraction. That would be the moles of, say, component A over the total moles. Just like 2A, if you remember this stuff from 2A. Okay, this is something you haven't seen before. This is the pure pressure. That means if this A was just by itself, what would its vapor pressure be? Okay, so that's what that number represents. If component A is all by itself in a beaker, and there's a pressure above the beaker, that's this number. This is usually a given. It's called the pure pressure, meaning the pressure of just A. And this is typically just given in a problem. Okay? So, I don't know if you vaguely remember, or if our sub Josh mentioned this. If he mentioned Dalton's law, it looks almost identical. Dalton's law would look like this. Okay? P total represents the total pressure of the gas. PA, same PA. Okay? Those are two the same. This is the partial pressure of A above the solution. And XA, they're both mole fractions, but they mean different things. So, let's say we have a container. Here's our whatever. Let's get a different color. This is the mole fraction of the gas is that mole fraction right there. So XA from Dalton's law that you saw before is actually, if you didn't know, we were calculating the mole fraction of a gas. Now let's get a different color pen. The mole fraction of the liquid is represented by Raoult's law. That's an A. So if you calculate the mole fraction of the liquid, we're talking about Raoult's law. And that's the difference between Raoult's law and Dalton's law. It's where you get the mole fraction. You get the mole fraction from the gas or the liquid below it. Okay? So, simpler problems would just involve this, and they're just the same as Dalton's law from before. They're actually a little easier, because you're probably not going to use the ideal gas law, like we did in 2A. Okay, so they're a little bit easier. We give you this number, you find the mole fraction, and you multiply them. So they're pretty much that simple. I'll do an example in lecture for sure. Dalton's law was harder, if you remember, in 2A, because we had to use the ideal gas law to get this. Sometimes we had to use the ideal gas law to get this one. And so it's a lot more steps to calculation. Now what makes the problems really exciting? If we combine these two. So I will do, that makes it a little bit tougher. I'll show one of those in lecture as well. Okay? So I think I'm going to pause right there for our general question time. If anybody wants to leave, go ahead. Get the heck out of here. Need to go watch The Bachelor or whatever. Check your Tinder account. And I will resume in just a couple minutes, and we'll do specific questions. Yeah.